Hey there everybody, this is one more video for chapter 4.3. Just a couple more examples that will maybe look a little different than the ones we've done before. And okay, so the first example is, and I think we're up to example 6 in our notes, find the critical points, intervals of increase and decrease, and the local maxima and minima of f of x equals 2x minus 3x to the 2/3. Okay, so first things first, let's get a derivative. So if we, there we go. If we're going to get the derivative of this, then f prime of x is equal to, let's see, the derivative of 2x is 2. The derivative of 3 to the 2/3 is negative 2/3 times 3. And then x to the 2/3 minus 1. So f prime of x is equal to 2 minus 3's cancel. So that's 2 x to the negative 1/3. And I'm just going to simplify that back into radicals. So that's 2 minus 2 over the cube root of x. And then, okay, now here's the thing. I'm going to probably have to make an interval chart for this. So it'd be easier if this was in some sort of factored form. So, and it would also be easier if it was not two different terms here, like, I have, term and term. It'd be easier if it was actually all kind of one term. So what I'm going to do is I'm going to, first of all, get a common denominator. So f prime of x is going to be, common denominator is cube root x, so that's 2 cube root x minus 2 over cube root of x. Then I'm going to factor it, and factoring this thing is going to give me 2 times the cube root of x minus 1 all over the cube root of x. And I think of this as factored, right? Because I know it's a divide, but you can also, of course, think of it, if you like, as 2 times the cube root of x minus 1 times 1 over the cube root of x. So it really is 2 factors. So this is the way here that I'm kind of going to think about it. This is the way I'm going to work with it. It'll work easier this way. So the first step, of course, is to set it to 0. And so, okay, so if we set this thing to 0, I'm going to maybe move over because my graph over here is kind of already coming out. So, okay, so let me recopy that. So f prime of x is 2 times the cube root of x minus 1 over the cube root of x. And, okay, what do I know? I know that if this thing, at places where this doesn't exist and at places where it equals 0, I have critical numbers for x. So, of course, f prime of x does not exist if x, or I shouldn't say if, I should say at x equals 0, right? Because then I'd be dividing by 0. So that means that 0 is my first critical value. And where does this thing equal 0? That'll be my next critical value. Okay, well, divide or multiply both sides of the equation by the cube root of x. Divide both sides of the equation by 2. Move 1 to the other side. Make a mistake. Sorry. And cube both sides. And x is equal to 1. So that means I have 2 critical values. And I'll call them critical values of x equals 0 and x equals 1. And I'll also figure out what those critical points are. Because after all, I'm going to want to maybe look at this thing on a graph later. And my critical points, let's see, run the 0 through the original equation. So the original equation is way back over here. There we go. So x is 0, and then y is 0. So my critical point for x is 0 is 0, 0. And for x is 1, I'd run that, I'd get 2 minus 3. So that's going to be 1 common negative 1 are my critical points. Okay, now, are those points local maxima or local minima? Well, I don't know. I'm going to figure that out by making a interval diagram. And again, I already have a graph of what this looks like, so let's not peek. So for my interval diagram, or interval chart, whatever you want to call it, let's see. So my furthest left critical point or critical number is when x is 0. So what's happening to the left of 0? What's happening between 0 and 1, which is my next point? And then what's happening after 1? So there's the 3 intervals I'd like to look at. And of course my 2 factors, obviously there is 3 factors, but 2 is not useful to think about as a factor because no matter what x is, that number is always 2. So that doesn't contribute to anything. So I have the cube root of x minus 1 as one factor, and the cube root of x is the other factor. And somebody asked me, well, wait a minute, those aren't factors, they divide each other. Yeah, but remember that the rules for multiplication of positive and negative values is the same for multiply as it is for divide, right? If you multiply 2 positives, you get a positive. If you divide 2 positives, you get a positive. If it's one of each, you get a negative. So the rules, it doesn't matter that they're divides. I still know that when they're the same, they're positive. When they're opposite, they're negative. So I can treat this chart the same way that I treated it in all of the other examples we did, where they weren't divides. And so that's going to tell me whether f prime of x is increasing or decreasing. Okay, so, well, if I let, okay, remember, let's take a look at what the function is that I'm running this through again. I'm running it through f prime of x is equal to 2 cube root x minus 1 all over cube root of x there, just to keep that kind of handy so I can see what I'm doing. Okay, if I pick a number that's smaller than 0 and I run it through here, well, smaller than 0 is a negative, and when you cube root a negative, you're still negative, so that's a negative. Once again, if I cube root a negative, you're negative, so a negative divided by a negative is positive. It's increasing. If I'm between 0 and 1, well, if I cube root a negative between, well, actually, sorry, hang on. If I cube root a positive, but it's smaller than 1, well, the cube root of that's going to make it even smaller still. So when I minus 1, I'm still going to be negative. But cube rooting that number, it is a positive. So a negative divided by a positive is a negative. So we're decreasing. And then when I'm bigger than 1, then the cube root of any number bigger than 1 will still be bigger than 1. So that's positive, positive, positive. We're increasing. Okay, I'm ready for a conclusion now. How about you? Therefore, I have a local maximum at the point 0, 0. And how do I know it's a local maximum at the point of 0, 0? Because at 0, we're increasing on the left, and we're decreasing on the right. So as we head up to 0, we're increasing. We hit 0, we decrease. That's definitely a local maximum. And we also have a local minimum at, what was the other point again? 1, negative 1. Because we're decreasing on the way to the point, and then we're increasing after the point. So there we go. That gives us a look at whether we have local maximums or minimums. We found them. That was the question. And just to kind of check with Desmos and the graph looks like this, which is interesting. Interesting, interesting. You'll notice that... oh, actually, that's not the right graph. Hang on. We're over here someplace. You know what? I think I just glued the wrong graph there. Yeah, let's see the... Oh, no, that's right. It is a local... No, that's right. You know what I forgot? I forgot that, oh yeah, this thing, one other thing that we know about it is that it doesn't exist. That means it's not differentiable at x equals 0. And that means, now, is it continuous at x equals 0? Yes, it is. It's not going to be an asymptote. So it's a cusp. So it's still a local maximum, right? Local maximum. And what was my local minimum again? Right there at 1, negative 1. So there we go. Local max, local min. And because it was not a differentiable point, because you know it doesn't exist there, the derivative didn't exist there, I should say. There we go. We have a cusp. And another way that you could prove that it was a cusp and not an asymptote is you could do the limit of this thing. Let me go back to the original equation. There we go. you could do the limit of this thing. If you did the limit as x approached 0 of 2x minus 3 to the, or x to the power of 2/3, and you approached it from the left and the right, in both cases, you don't go to infinity. You actually, and the limit as x approaches 0 from the left of 2x minus 3x to the 2/3. As you do the limit from left and right, both of these things, you end up with 0. So that's actually something that's going to be in the next lesson. So that's another way, or that's kind of the most important way that we could tell that no, there wasn't an asymptote here because you're dividing by 0. The problem here is that in the original equation you're actually not dividing by 0, right? It's not really a division by 0, so it's not an asymptote. It's not that x can't be 0, but I can't differentiate it there. So it's not an asymptote, it's a cusp. Cool. So that was example 6. Example 7, find the local maxima and local minima of f of x is equal to x plus 1 over x. Okay. So once again, I'm going to approach it kind of the same way. I'm going to find my derivative. Before I do that, I'm just going to rewrite this as x. Let me make that a little bigger, easier to write with. X plus x to the negative 1, right? Negative exponents are easier to deal with than fractions when I'm doing my derivative. After my derivative, I'll probably switch back. So that's going to be 1 plus negative 1 times x to the negative 2. So let's tidy that up a bit. That's 1 minus x to the negative 2. And I think I'm going to go back to a fractional form, rational form. 1 over x squared. And again, I'm going to make that same decision. Now, why am I making this decision? Because, oh yeah, eventually I'm going to need to do an interval table. And it'll be easier to do that if that's in some sort of single term or single expression instead of two different terms. And it'll be easier if it's something I can factor. So once again, using common denominator, I'll work up here. F primed of x, come on pen, is equal to x squared minus 1 over x squared, right? I just times this 1 here by x squared over x squared. And so that's going to equal, f primed of x is going to equal, like I said, it's better if I factor it, x plus 1, x minus 1 over x squared. Now, let's see what we can do here. Now, in this case, x equals 0 definitely is an asymptote, right? I might even write that down. X equals 0 is an asymptote. Asymptote, right? You can't actually be 0. Actually, that's not the only asymptote. Because x equals 0, notice that 1 over x can't equal 0. Therefore, y cannot equal x, right? Because remember, the original equation was y equals x plus 1 over x. So if, again, let's see if you can follow the logic here. If this thing can't be 0, then there's no possible way y could just same old equal x. So that means that, that means that I'm trying to write with the highlighter, sorry. That means that y equals x is also an asymptote. But what kind of an asymptote is y equals x? Well, it's a oblique or diagonal. The word diagonal actually does apply to this, but it doesn't apply to all things that are not horizontal or vertical. But in this case, yeah, it is a diagonal asymptote. The general term for all non-horizontal or vertical asymptotes is oblique. It's an oblique asymptote. That used to be something we did for a lesson or two in the old grade 12 curriculum, but they kicked it out. But it pops up in calculus all the time, as you're going to see as you go further into calculus. Anyway, what am I doing with this? Oh yeah, I want to find the local max and local minimum, right? So that's my goal. I already know some things about this shape. I know it has some asymptotes, one of which is kind of a diagonal, which is cool. But getting back to the derivative, remember that the derivative is, of course, going to be, well, let's see. My critical, oops, and I just misspelled critical. Let's try that again. My critical values, well, again, where it doesn't exist, x is 0, because, again, can't divide by 0. And then the other ones are going to happen when f of x is set to 0. And when I set that, and notice I'm working with the one that's easier to work with. This is going to be the easier one to work with over here when I'm going to my table for my intervals. But just to figure out my critical values, might as well use the one that's less algebra. So I'm going to move this to the other side. I'm going to divide or times both sides of the equation by x squared, and x is equal to plus or minus 1. So my critical values are x equals 0, x equals 1, and x equals negative 1. Now we already talked about how this one is definitely an asymptote, so it doesn't exist. But what about the other points? Do they exist? If I go back to my original function and I plug in a 1, I get 1 plus 1, so this is the point 1, 2. And this is the point, plug in negative 1, and I get 0, right? So I get negative 1, 0 if I plug back into the original equation. Okay. So we've got critical values. Might as well say we also have critical points. One of them's a critical value, but not a point. And yeah, I think we're ready to make our interval chart. What do you think? Let's make an interval chart. So my interval chart, interval chart. This is going to be a little longer, actually, because I have 3 values. And let's see, and my 3 factors are, there's the factored form again, x plus 1, x minus 1, x squared. And f primed of x, what's it doing when I go through all those factors? And are we increasing or decreasing? So here we go. My interval chart for this thing. Let's start with the furthest left, which is negative 1. Excuse me. So what happens when we're left of negative 1? Left of negative 1. Okay, that would be negative, because this is smaller than negative 1. That would still be negative. That, of course, would be positive. So a negative times a positive, or I guess maybe I should say a negative times a negative divided by a positive, will be a positive. So that would be an increasing zone. Increasing interval. I should use the word interval. If I'm between negative 1 and what was the next one again? A 0. Okay, so I'll have to work with a half. No biggie. Negative a half here would make that still a positive. It would still keep that a negative. You can't get anything but positives on this one. So a positive times a negative, but then divided by a positive is negative, so we're decreasing. Next interval. What happens when I'm between 0 and 1? Okay, so between 0 and 1, so that's a positive. That's a negative. Still positive. And we're a positive times a negative times a positive is negative. Hold the phone. We're decreasing again. We warned you in the notes earlier that this might happen. There's no change, so this can't be a local maximum or minimum. Okay, anyway, let's finish it off. X is going to be bigger than 1 is my other interval, basically the rest of the graph. That's definitely positive. That's definitely positive. That's never not positive. And so that's positive, and we're increasing again. So what is my conclusions here? So therefore, the point when I'm at x equals 0, when x equals 0, actually let's do them in order. When x is negative 1, or at the point negative 1, 0, I should say, we switch from an increasing to a decreasing. So increasing, decreasing is a local max. So there's one answer. When x is 0, we go from decreasing to decreasing, not a max or min. It is not. What is it? Well, we actually already know. It's an asymptote, but it's not a local max or min. And finally, when x is 1, we switch from decreasing to increasing. So if you're decreasing, then you're increasing. I should say, therefore, x equals 1, which is, of course, the point 1, 2, is a local minimum. And there we go. There's our answer. You want to see what the graph looks like? I put it on here somewhere. Oh, there it is. It's this guy. Isn't he interesting? And like I told you, the point 0, negative 1 is a local max. the point 1, 2 is a local min. And remember, we found out that 0, when x is 0, it was a critical point, but it was definitely not a local maximum because it did happen to be a vertical asymptote. And like I was pointing out to you, there is an actual diagonal asymptote. I should make that a dotted line. How silly of me. Oh, I can't just erase that way. Make that a dotted line because that is an asymptote. And there we go. Get used to graphs like this. They pop up a lot. Okay, so there's our last 2 examples for 4.3. This little part up here that I was kind of playing with here, going back to limits, that's what we do next. Next we go back and review limits, and you'll join me in Chapter 5. Okay, thanks for watching the video, guys.